We had finished up the previous video looking at Young's experiment, which was light wave interference through two slits. And in fact, this was the observational evidence that led to the final acceptance of the wave model of light. Now, as I've said, Newton did get his particle model revitalized with the advent of modern physics, where we now accept that the dichotomy between waves and particles is a false dichotomy. And by the way, his concerns about the diffraction on the edge of a shadow, that turns out it actually does happen, but because the wavelengths of visible light are so short, there was no way that he was able to see that. Anyway, I'd like to extend the application of Young's experiment a little further. So you might ask yourself, what if I had more than two slits? Well, if you have a whole bunch of slits, typically very close together, then what you've done is you've made yourself a diffraction grating. So these are a whole collection of slits here, and it works exactly the same way as Young's experiment. So you'll have plane wave of light coming in on the diffraction grating, but then it'll be the exact same deal. You'll have a central maximum here, but now the first maximum, or the first order spectrum, will be way off to the side typically, and then the second, and so forth. The reason why the much larger distances than you would have for Young's experiment is that in practice the spacing here is quite small compared to a typical double slit experiment, and this is going to lead to us not being able to use small angle approximations. But it turns out it's the same deal. So you'll have light, say, coming from, let's just look at these three slits here so we don't get too confused. Say if I look at light coming in from these three slits here and here, these two have a difference of 0 wavelengths. And you could say do this pair and that pair, and it'd all be 0. And you could play the same kind of game, say, over at the first minimum. If I look at the light going from here to here versus here to here versus here to here, these two would have a difference of 1 wavelength, just like before. And these here would also have a path length difference. Call it L3 minus L2, I guess, of 1 wavelength. So that means these two here, this distance here will be 2 wavelengths longer than this one. But that's good. That's still going to have crest meeting crest or trough meeting trough. And here the differences would be like 2, 4, 6, 8, and so forth. So it turns out that the behavior is exactly the same kind of behavior as Young's experiment. But like I said, the difference here is that typically, for typical practical diffraction grating, the slit spacing is very small. And so that means it's actually it's actually small enough that the angles involved will be large. And this is by design. The larger you can make the diffraction angles for spectroscopy, it'll turn out, the easier it'll be to pick out individual colors of light when we get there. So what this means is it's the same kind of derivation we had for Young's experiment. I'll just quote the result here. D sine theta m, where m is the order of the spectrum, equals m lambda, and y equals L tangent theta m. And this is for m equals 0, 1, 2. And in practice, you usually don't get much above the second order, maybe the third for some setups. And this is because the angles are just so much bigger. So why would we want something like this? Well, it turns out that, all right, at the 0th order, if you have light that's just made up of a few specific colors, then at the 0th order they'll all land right there. But what's going to happen here is, because the angle does depend on the wavelength, if you're teasing apart different colors of light, the longer wavelengths will go through bigger angles. And that's really where we're going with this. The other thing that happens too with these diffraction gratings is you'll notice that I drew in a lot of very dark area here. Now the derivation of this is tedious, so I'll just kind of motivate it a little bit. But you can show that the maximum intensity of light that you'll have at any particular peak goes as the square of the number of slits that's illuminated. However, the total available light, the intensity of the total available light coming in, is going to go just as the number of slits. So if the peak brightness is getting brighter, that means we have to have larger regions that are dark. And again, for the application of spectroscopy, this is a good thing. You have very narrow places that are lit up, and then most of it is dark, so you can easily pick out the exact angle that the light is being scattered through, and then figure out the angle. So in this picture here, what you are looking at on the left is actually the 0th order spectrum of the light coming from a helium discharge tube. So this is like those old neon lights, except instead of neon being in the tube, it's helium here. And so the 0th order spectrum just looks like the helium tube, which it should, because every single color of light that's being emitted by helium is passing right through. Now, the camera is looking through a diffraction grating here, and so you can see some colors sitting off to the right. These are the colors, these are the individual colors that are being emitted by helium. Those colors are emitted, and only those colors, which is what gives helium its unique color when lit up. Why only those specific colors? Well, that gets into quantum mechanics, but the short answer is that their helium has a unique electron structure compared to any other atom, and atoms going back and forth between the places it's allowed to be in, that quantum mechanics allows it to be in, gives it this unique fingerprint of colors. And so if you have some unknown sample, you can use the spectroscopy. You can use spectroscopy to tease apart the individual colors of light and work out the wavelengths. And from that, you can work backward what the electron structure has to look like. Similarly here, this is the exact same picture, except instead of the tube being filled with helium, it's filled with hydrogen. And you can see that the hydrogen has a distinct color, and that the individual colors that make that up are different. And again, this is due to the unique electron structure of hydrogen. Alrighty, so in the next series of videos, we will start to concern ourselves with single slit interference. Catch you over there.